Alright, here we are back again for part number 2 of June 14th, 2016. So I just have a few example problems I'd like to work through applying principles of couples. Principles of couples. So in the previous portion of the lecture, we learned what a couple was, and today, right now, we're going to work on applying them. So this is problem 3.73 in the Beer Vector Mechanics book. This is, if anyone has any questions, this is Beer Vector Mechanics 10th edition. It's actually just, the full name is Vector Mechanics for Engineers 10th edition Statics by Beer, Johnson, and Mazurek. But anyway. So problem 3.73. A piece of plywood in which several holes are being drilled successfully has been secured to a workbench by means of 2 nails. Knowing that the drill exerts a 12 Newton-meter couple on the piece of plywood, determine the magnitude of the resulting forces applied to the nails if they are located at A and B, B and C, and A and C. So, let's see where this takes us. Just take this at face value. So what we have here, let's see. Let me draw a free body diagram of this from above. I think that'll be a lot easier. This looks like a 3D problem, but this actually can be reduced to a 2D problem. So note, they do not give us the location of the drill. And because it's only introducing a couple, it's not introducing any lateral or vertical forces. In reality, a drill probably would, but we're going to ignore that. It's only introducing a it is not introducing any kind of translational force, only the rotational force of the couple. So the way I'm going to draw this is I am going to show a let's see. I'm going to have a couple here, which is an arbitrary couple here, and then at point then there'll be points A, B, and C. A, B, and C. So let's consider the first case, where we have the couple and it's and this plate, this piece of this board, is secured at A and B. Now, here's the question. So let me draw the board again for part A. Consider this for a moment. Can I figure out what directions these forces must be applied? Let's see. Just by eyeballing it? I bet I can. So I know that I'm going to have some sort of force at A and some sort of force at B. Will I not? I have to. I have to have some sort of force at A and some sort of force at B resisting this. Now, let us think about this. I know that these forces, I have 2 forces and only 2 forces here. I have a force at A and a force at B. However, these forces have to be equal and opposite. They simply have to be. The reason they have to be equal and opposite is because this is not introducing any translational force. So in other words, if I had forces like this and, I don't know, just non-equal and opposite forces, just like arbitrary forces like this, there would be a net translational force on this object, yes?
Sorry, since it's positive 12, wouldn't it be counterclockwise?
Let's see. Well, it doesn't. I guess, yeah. The question was, since it's positive 12, does it matter which way we draw this? Technically, all they're asking for is the magnitude of the forces, but you know what? Why not? Since I'll just go ahead and make it counterclockwise instead of clockwise, just for sort of convention's sake. That's fine. It won't ultimately matter because they're asking for the magnitude of the forces, not their directions, but that's okay. I'm happy to oblige. Okay, so these forces as drawn are not going to work. simply because they are not equal and opposite. They are going to introduce some sort of translational force, which, since there's nothing to resist that translational force, the board's going to go flying through the air. This would not remain in static equilibrium. So what else, what other options do we have? So this isn't going to work. Instead, these forces must be equal and opposite. It keeps erasing my other lines. These forces must be equal and opposite. So I have my couple here, which that is a really bad drawing. Ugh. Couple. Then I have these points here and here. They could be equal and opposite. I could have like a force going into here and into here. That would be equal and opposite. That wouldn't introduce any translational force. However, if I do that, there's not going to be anything to resist the moment here. In other words, if I put a force this like from here to here and here to here, there's nothing to resist the rotation of this, so that it's just going to rotate about. In other words, if I draw this and this going into A and B, these two, say if I take moments about say this point, these two are going to cancel each other's moment out, because they're going to have the same perpendicular distance. If I some moments about this corner here, I could see that they're going to cancel each other out. They're not going to be able to resist this moment here. So what we can actually see, if we think about this a little bit, is that, oh my goodness, I keep erasing my own drawing. What's going to happen instead is this couple is going to be resisted by another couple. So I'm going to need something like this. Now we can think about this. So that we need to have two forces that are in equal and opposite direction, and they have to be in equal and opposite again because we can't have any kind of translational net force on this. And because we now have two equal and opposite forces separated by distance, we have a couple, and this couple can resist the rotation caused by this couple here. And the question, this brings up the question: will it be this one going up and this one going down? Or this one going down and this one going up? Well, if I look at this, these together will tend to cause a clockwise rotation, will they not? And so if I have this drawn as a counterclockwise rotation, these two must be able to cause a clockwise rotation. And so, you know what, I could do a big sum of moments, but I can actually just say, oh, this is just a couple. So moment is going to be force times distance. The force is going to be the moment, which is this 12 Newton meters. The moment over over the distance. These are separated by sorry about that. These are separated by 450 millimeters. So this is 12 Newton meters over 0.45 meters. And that comes to 12 over 0.45, and I get 12.67 26.67 newtons for part A. For part B, the same idea is going on. We have the same idea. Let me draw the forces on here. I'm going to have this point and this point, B and C. I have the same moment, and I'm going to have, okay, equal and opposite forces. However, I'm going to need a force, this is again causing a counterclockwise rotation, so I got to set these forces up such that they will have a clockwise rotation, like this, F, F, and here the force is again just equal to moment over the distance, so that's going to be 12 Newton meters over a distance of 0.24 meters, which will be 50 newtons. Finally, for part C, I'm going to have the same plate and the same moment. The same moment applied here. But I'm going to have this point here and this point here. So therefore, I'm going to need to have a force system like this. Again, causing clockwise rotation. These two are going to work together as a couple to resist this one here. And the distance will require a little bit of work, but not much. Distance is just the Pythagorean. And I know I like to use the term the Pythagorean, but I know that's not proper math, but oh well, this isn't math class. Plus 0.45 squared, which is equal to which is equal to 0.51 meters. And then therefore the force is going to be equal to m over d, 12 Newton meters, over 0.51 meters, which will come to 23.5 newtons. 23.53 newtons. So we can see a behavior here. We need to have two forces resisting a moment. And we can see that the larger the distance between the 2 points, between the two forces, the less force that we'll need. This is the principle that you see if you look at, say, a tire iron, like we discussed before. If you have, say, a tire iron, this is a very crudely drawn tire iron. If you have a tire iron is used to remove the nuts on a tire, obviously, to change the tire, etc., etc. And if you have a, the whole point of this is that it's to generate moment. It's to generate moment, or if you're not talking engineering, it'd be to generate torque. So if you sit here with your hands and try to manually remove the nut on a tire bolt using just your bare hands, you're going to have a hard time. Now, maybe there's some extreme, Olympic strongman out there who can do that. Maybe there is, I don't know. But I, for one, can pretty much be assured, I can pretty much tell you that I cannot, and most of you probably cannot, remove a tire without just using your bare hands. If you can, I would be very impressed. But anyway, the whole point on this is to give yourself a moment arm. You're going to apply a force, say, like this way, and this way, this way, and this way. That would be to tighten it. To actually loosen it, let me draw this in red. To actually loosen the tire iron, we want to make it go clockwise, or counterclockwise, sorry, obviously. So we want a force like this, and a force like this. Oh, actually that will loosen it. Oh, not thinking right. So yes, we want to apply a force like this with one hand, and so an upward force here with our right hand, a downward force here with our left hand, and that will generate the moment needed to overcome the resistance in the bolt. Okay? Anyway, now if you have a, what can you do if you, what can you do if you find that even with the tire iron, you still don't have enough strength to open the bolt, or to turn the bolt? Huh? Could use your legs, or well, actually, you know what? It just so happens that I just so happen to have a metal pole lying by. I just so happen to find a metal pole lying by the side of the road, and so I'm just going to come along and attach a 8-foot metal pole.
You call it a cheater bar.
Yeah, a cheater bar is what you see in sometimes in the iron workers industry. A cheater bar is sometimes that you hear. Any method you can use to give yourself a longer moment arm. What's the one thing you got to be careful of though when you're using a long cheater bar?
Smacking your hand into something?
Smacking your hand into something, that could happen. No, actually, one major problem is, okay, if you say, well, if a 3-foot cheater arm is good, a 30-foot cheater pole will be even better. Well, you might just come along and just shear the head right off that bolt, and then you're going to have a real bad time. Anyway, and you're going to have to, oh man, that's not going to be a happy day. Okay, so that's that. Any questions on this? This is a fairly straightforward application of couples.
Sorry. So that would mean that the instantaneous moment of on that bolt is greater than the bolt's ability to rotate?
Okay, if you sheared the bolt off, what's actually happening is, let me go, actually, I like talking about this, that's fine.
Friction on the bolt, I mean?
Let's see, bolt shear. This is structural engineering, or a bit of mechanical, I guess. So,
We're all engineers here.
yeah. Okay, so say you have an enormous, say you have a bolt, and you're going to apply an enormous, now you'll learn about this when you take mechanics and materials, which is a course after dynamics. So you apply a large moment to the bolt. Now I probably shouldn't draw that as, you know what, I'm going to be a little less lazy. Maybe I'll draw this as a hex bolt instead of a circular bolt. Let's draw a little hex bolt here. Something like this. And if this is looking at it from the front, and from the side, it's going to look something like this, right? It's going to look something like this. This is a very crude representation of a bolt. Now, when you take, so in statics class, we consider objects as rigid bodies. We say an object has effectively infinite stiffness, infinite strength. But when you get to mechanics and materials, you will abandon that assumption and start looking at, oh, how much strength can a material actually take? And that's where you get into things like, if I look at the, say, like the circular, where this would fail would probably be right here. That'd be the weak point, most likely. And if I look at the circular cross section here, oh my goodness, I cannot draw a circle today. Let me try again. If I look at a circular cross section, so yes, this isn't really static, but that's okay. What I'll have is, I will actually end up with something like, you'll actually have a stress distribution, that it's large on the outside of the bolt and decreases as you get toward the center. So you have a very large amount of stress in the material on the surface, and as you get, because, in other words, the fibers of the bolt are in shear, and that will, and while they are in shear, that is actually producing an internal moment inside the bolt. And this internal moment must be able to resist the moment that you're applying. And this would be like an elastic condition. But then if you add a plastic condition up to the limit of the bolt, up to say the elastic limit, you could have something like this, where you're just torquing the hell out of it all the way to the plastic limit. And at this point, shortly after this, you'll have passed the ultimate strength of the bolt, and that's where the thing just gives up entirely, and you just take the head right off the bolt, and it's going to break.
Brittle fracture toughness?
You can end up with like brittle hardening and things like that, but I'm talking just purely shearing here. It's pure shearing the bolt right off. So yeah.
That's assuming though that the bolt will not start to unscrew, right?
Yes. That's again, we're assuming that the bolt will not start to unscrew. Now, okay, so the question is, why wouldn't the bolt just unscrew? The reason for that is maybe the bolt's really tight in there, but more importantly, you're applying such a large moment that doesn't even have time to break the bonds. It doesn't even have time to transfer the force all the way through the bolt before it breaks off.
Is it kind of like you have to, in order to overcome something moving, you have to go past static friction, so in order to move the bolt, you have to go past a certain moment?
It's more like forces do not transfer in non-zero time. So if we're using our ridiculous 50-foot long cheater bar or something like this,
Yeah.
Okay, so the grooves of the bolt are back here, right? And it's actually secured back here. If I apply an enormous force here, an enormous moment here, it needs time for that moment to make its way all the way back. And once it does, yes, it will release the moment by turning. But if it's if there's not enough time for that we're talking fractions of a second here. But if I apply that force, say, too quickly, then that's where you really get in trouble. So yes, you could use an enormous cheater bar, but you would want to be very careful to apply force very slowly. So apply a small force and then gradually ramp it up until you're at the limit of your strength. You wouldn't want to just instantaneously just shove down on that thing with as much strength as you have, because it doesn't have time, and it doesn't have time to transfer the load, release the moment, and it will just break off like that. Does that kind of make sense? It's a time delay thing, actually. So yeah, this has nothing to do with statics. Well, it has a little to do with statics, but so to actually properly understand why a bolt shears, you need to actually treat it as both a mechanics of materials and a dynamics problem. So anyway, but don't worry about that. That's okay. So so it's actually quite complicated. Even something as simple as a bolt, you can actually get into very complicated analyses. Let's see. Let's look at this here. A 30-pound vertical force P is applied at A to the bracket shown, which is held by screws at B and C. Part A, replace P with an equivalent force couple system at B. And then Part B, find two horizontal forces at B and C that are equivalent to the couple obtained in Part A. So we want to obtain an equivalent force couple system. So Part A. So I have a force at P. So let's look at this. Let me draw a free body diagram here. It's actually not quite. Wouldn't be a proper free body diagram. I'm just considering. I'm not trying to consider all the forces here for Part A. I'm just trying to replace it with an equivalent force couple system at B here. Well, the equivalent force couple system is going to be equal to the vertical force plus the moment generated by that force at point P, or at point B, I should say. So the equivalent, so let's say this is equivalent to this. This is equivalent to the following system. £30 here, and a couple of, let's see, the force here is 30 pounds, and the distance is 5 inches, so 30 times 5 would be 150 pound-inches, correct? 150 pound-inches. So a 150 pound-inch couple. So
It's 2 inches here, right?
no, it's actually 5 inches, because we don't want to use 2 inches. We want to use 5 inches because this is a vertical perpendicular distance. Yes.
Why are we using the hypotenuse?
Because we're looking for the perpendicular distance. Perpendicular distance. Okay. Now, so what makes this a couple rather than just a moment? Well, let's look at this. What could I do with this? I could say this is also equivalent. It doesn't matter where I apply this moment for here. I could say that it's also equivalent to this. This moment is not just a moment, it's a free moment. I could have a 30-pound. I can't move the force around without changing things, but I could move the couple around very easily. I could put it over here. I could put it over here. It doesn't matter. A couple can be moved anywhere you please. Questions on that?
I don't understand the whole 30-pound being directly. That's like if I put 30 pounds on a bolt, rather than 30 pounds on the end of the.
Okay, what's happening here is, again, let's go back and review this. You don't understand, what don't you understand exactly?
How's the 30-pound creating a 150-pound
Ah,
force directly on it, not using the lever arm?
it's not creating a, okay, we're just saying, in other words, if I apply, well, all we're saying is this system is equivalent to this system. That's all we're saying. So this thing would, this bracket would experience the same tendency to translate and rotate if I applied a 30-pound force here, or if I applied a 30-pound force at B and applied a 150-pound inch couple at B, or moment at B, okay? Or a 150-pound couple anywhere else, actually. So, okay. Other questions?
A question. So from the second part to the third part, did you move the force down or did you move the force stayed the
The
same,
force
right?
stayed at B.
Okay.
Anytime we move, the question was going from here to here, did I move the force? If you can't tell in my crappy drawing, no, I did not. Anytime you move a force, the couple will change, the accompanying couple will change.
Okay.
But the couple can be moved wherever you please.
Okay.
It's only when you move a force, because when you move a force, then you're shifting moment arms around, and so then you would need to worry about that. Now B, find the two horizontal forces at B and C that are equivalent to the couple obtained in part A. Well, the couple, we need a 150-pound, a positive 150-pound couple needed. So if we consider B and C, let's see. So we have a, now I don't want to resist this, I actually want to find an equivalent. So I have a 150-pound inch couple. So I want this actually going in the same direction. We have to be careful of the, we have to be careful of what we're asking for. So we have a force here and a force here. So again, it's asking for two forces that are equivalent. If it were asking for two forces that will resist this, I would actually want it going the other direction. See, this force and this force together are going to create clockwise rotation, or sorry, counterclockwise rotation, just like this 150-pound inch couple will. So we're trying to find an equivalent system, not find a balancing system. And so then we can simply say, this is a couple again. We can just go back to the definition of a couple. Moment is FD. F equals M over D. 150 pound inches over 3 inches equals 50 pounds. 50 pounds of force, and that will be our answer. So we have a 30-pound force down here, and that's going to be equivalent. In other words, the let me actually show it like this, perhaps. I can have another set of equivalent systems. Actually, let me show like this, equivalent. Well, I would still need to have the, I would still need to have the vertical force applied here, right? Because that's not going to change. 30 pound there. But then, 50 pound and 50 pound. So in other words, the bracket will behave exactly the same if I applied these three forces to it as if I applied this force to it. These are equivalent systems, at least in terms of statics. If we got into not necessarily dynamics, if we got into mechanics of materials again and started analyzing actual stresses in this thing, that would no longer hold true. But anyway. Questions on that? Yes.
So we are, with our couple, we're generating the 30-pound force, right?
With your couple, you're generating the 30-pound force? No. The 30-pound force is the 30-pound force. If I'm simply saying in part A, if I wish to move the force to part B, what's the equivalent force couple system look like? And that would look like a 30-pound force with a couple applied. In other words, this will cause the same behavior in the bracket. If this was floating in the vacuum of space, this would behave with the same translation and angular acceleration. It would go down like it would, if this was just floating in space, it would go flying downward and it would also start rotating, right? Same thing as this one. But in other words, if I had two brackets floating in the vacuum of space, and one I applied a 30-pound force downward here, and one I applied a 30-pound force and a couple or a moment here, these two would behave exactly the same. That's what we mean by an equivalent force couple system. Yes?
You just got 150 by multiplying 30 times 5, right?
Yes, 150 is just 30 times 5. Yes.
So is this kind of also saying in effect that it'd be harder to rotate that if you tried to move it at B?
The question is, would this basically say it'd be what?
I'm just trying to conceptually understand it, because like basically, you could create the same effect, just applying 40 to, 30 pounds, but if you try to move it at B, you'd have to both apply.
Perhaps, I don't know. If that helps you conceptualize it, perhaps. I don't know. Maybe. Okay, other questions? Okay, moving on.
Left-hand side there on part A where you're applying the 30 pounds off to the side, there's no torque showing there, right?
No, because we're now, yes, in reality, when we get to the next chapter, we'll actually be looking at two-dimensional equilibrium, or rigid body equilibrium, and that's probably what's bothering some of you, because you're looking, oh, there must be some other force to balance this thing. But we're not trying to find the equilibrium here. We're not trying to say what other force must be added to this to keep it in equilibrium. We're just saying what force couple system is equivalent to just this one force. Okay? So, as it's drawn, no, there's not a moment on here. There is simply, all I'm saying is this is equivalent to this. That's really all I'm saying. That's it.
So the 30-pound generates a moment about B.
The 30-pound will generate a moment about B of 150 pound inches, yes.
And moving it, the 30 pounds, to that, in addition to the moment generated by that couple.
Would be the same, yes, yes, yes. Okay. All right, three-dimensional time, or 3D time. Joy. Okay, 3.93. An antenna is guided by three cables as shown. Knowing that the tension in cable AB is 288 pounds, replace the force exerted at A by cable AB with an equivalent force couple system at the center O of the base of the antenna. So we have this force here. Let's see, AB. Oh, this is ugly. Force exerted at A. Oh, okay, at A by cable AB. So we want this force here, basically, right?
Down.
And it's going to be down because this is in tension. And this is our F. So what we want to do is we want to move this down to the origin. So we're going to have obviously we're going to have a force here, the same magnitude and direction as this F, same F. But we're also going to have some sort of moment vector. And we'll find that. And that moment vector is simply going to be R cross F. So we want to find an equivalent force couple system. So first, a lot of this is going to be some repetition of some things we've done before. I'm going to need the coordinates of A and B. A has coordinates 0, 128, 0. B has coordinates That looks like, let's see, negative 64 feet, comma 0 feet, comma, that looks like 16 feet, right? 16 feet. Then we want AB. I want to get the force vector F. Force vector F is going to be equal to 288 pounds times lambda AB, the unit vector from A to B, because that's where because we're asking for the force exerted at A along the line A to B. So let's find that. First, I'll find the overall vector AB. So maybe I'll call that RAB. That's simply going to be B minus A, the coordinates of B minus coordinates of A. So that's going to be negative 64 feet, comma, negative 128 feet, comma, 16 feet. Then lambda AB is going to be, let's see, negative 64 feet, comma, negative 128 feet, comma, 16 feet, like so. All of this divided by the magnitude, which is 64 squared plus 128 squared plus 16 squared. And then let me throw that in a calculator. Do that really quickly. Negative 64, comma, negative 128, comma, 16, divided by the square root of 64 squared plus 128 squared plus 16 squared. And I get a unit vector of negative 0.444, comma, 0.889, comma, 0.111. That's the unit vector of the force's line of action. Huh? Oh, thank you. Yes, the y component of the unit vector should be negative. Yes, thank you. Okay, then the force vector is just going to be 288 pounds times, as a scalar multiplier of the unit vector, 0.111. So it's multiplied by 288. And this is negative 128 pounds in the x, negative 256 pounds in the y, and 32 pounds in the z. And now we need, in order to find the moment generated by F about point O, I need the vector from O to A. R is just going to be ROA, and that's just going to be 0, comma, 128 feet, comma, 0. So then, let's see here, 0, 128, comma, 0, and I'm going to be lazy and just, well, not quite yet, I'll be lazy in a bit. The moment is going to be R cross F, which is going to be 0, comma, 128, comma, 0, crossed into negative 128, comma, negative 256, comma, 32, and that's going to be equal to, let's see, 0, 128, comma, 0, and let's do the cross product of those. And I know I could do this fairly easily, I'm just being a little lazy here. This and I get 4,096 pound-feet, comma 0, comma 16,384 pound-feet. So, my final answer would be the equivalent force couple system at O, at the origin, would be a force vector of negative 128 pounds, comma, negative 256 pounds, comma, pounds, comma, 32 pounds, and a moment of 4096, comma, 0, comma, 16,384. 16,384, all of this in pound inches. And this entire thing is our solution. In other words, if I wanted to move this force down here, an equivalent system would be this force vector and this moment vector.
Just the subscripts on both the force and the moment would be O, right?
Subscripts are somewhat arbitrary, but I guess I could just call this moment at O. I could call this one OA, and this is just the force that we found earlier.
I'll let him answer.
Oh, and here, yeah, if I wanted to use subscripts, I guess suppose I could call this like force O and MO, but I'm not really that picky on subscripts. Yes?
Which one did you say is for the test? Is it like, like 30% chapter 2 and 70% chapter?
The test should have things pretty well spread out throughout the material. So, okay. All right, other questions? Yes.
So you're never going to try to change the force. It's just going to you're finding the moment to balance out that.
The question is, we'll never try to change the force, right? Yes, if we have a if we're just asking for an equivalent force couple system, no, we'll never end up changing the force. All that we do is add a moment to, we only add a moment to compensate from the moving the force to a different location. Or adding a couple, I should say, not moment. Other questions? All right. Okay. So I think that'll do it for today. We're gonna get out a little early today. That's okay. I'll give you a little extra time to prepare for the exam, etc., etc. So again, we will have the exam properly at 11:45 tomorrow. Give us just a little extra time. I'll try to get here a little bit before to give you to answer some last-minute questions if you have any. I will be throwing the solutions to the homework up on the website fairly quickly to give you some time to study those, including the assignment for today. I'll just throw those up right now, actually. And if you need any assistance, I'll be in the office till 4 or so. And I'll see you all tomorrow for the exam. Remember, we will have the exam from 11:45 to 1:45, followed by a short lecture, rather short lecture, just going over some brief new material. That should do it. Get some rest tonight. Study everything pretty well. If you need assistance, I'll be in the office. That should do it. I'll see you tomorrow. And as always, thank you.